get started here, I want to demonstrate how to do these problems, these mean chart problems. They can be a little bit tricky, and so I wanted to step through them using a little bit different technology, allowing me to actually demonstrate these. So there are a few types of problems we'll do in this chapter. This video will specifically focus on two of those types, or the X bar charts, which are mean charts. There's two styles of those. I want to demonstrate both of those. So we talked about this previously. We can either measure attributes or variables. Be clear on which one you're doing. Attributes are things we can count. How many people fell down the steps? How many people failed a course? How many? Count. Variables are things we measure. So if we were looking at GPAs, that would be a variable. We'd use a X bar chart. If we were looking at attributes like how many people got an A or how many people failed the course, that would be a count chart. We'd use some different tools. We'll get to those in a separate video. In this case, we're going to look at variables: height, weight, density, depth, volumes, things we can put a specific measure on, not a count. So, control charts for variables, these are called mean charts. There's two kinds. There's mean charts and there's range charts. First, we're going to focus on mean charts. We also call them X bar charts. So if you remember from statistics, from your statistics course, X bar is what we term the mean of the sample. So that's why we call these X bar charts. They monitor the central tendency of the process. So if we're making coffee, we're at Starbucks and we're a barista, we are making all this coffee. There's a right temperature for coffee. I didn't look it up, but I think it's around 180 degrees. You can look it up. You can just Google espresso temperature, but just for argument's sake, let's say it's 180 degrees. We want to know that coffee is being produced at the temperature people expect it to be. And you can use a control chart to do that. And so we would want to set up, we know 180 is the target, but there's some variation. The temperature of the incoming water, the number of cups of coffee you made that hour, the altitude of the store, the ambient temperature, the humidity, all these things affect the temperature that the machine produces. So we know there's going to be a little bit of variable. Our question is, what's an appropriate top limit and lower limit? And let's say we calculate this and the top is 185 degrees and the bottom is 175 degrees. We would hope that given our process that our coffee is between this, because our customers will be happy. We will consistently meet or exceed their expectations, if you remember that definition. So at 9 a.m., we might go out and take samples of 10 cups of coffee, and we'd stick the thermometer in each of those 10. We would write down those 10 temperatures. We would add them up and we would average them. That would be our X bar for that sample, the mean of the sample. And we would take that sample mean and we'd post it on our control chart. And at 10 a.m., we'd do the same thing, and we would get a slightly different number. We'd post that. And as long as it's between the upper and the lower control limits, we would say our process is in control. Everything's going as planned. But if at, let's say, 11 a.m. we go out and pull our sample and it's right there, that is below our lower control limit. Our process is out of control. We run screaming out to the barista and we say, what are you doing? Is the machine set correctly? Is the water coming in from the pipes correctly? Are you doing the job correctly? Is this a training issue? Is this an equipment issue? Is this a raw materials issue? Do you have the right cups? We would find what went wrong. We call it assignable variation. We identify the source of that variation and we fix it. And then at noon, we go get samples again, and we hope that now we're back where we should be, between the upper and lower control limits. So when we do these problems, the first thing we're doing is we're trying to figure out what the appropriate upper and lower control limit is. And once you figure out what that is, you don't change it. You put that in your system, you mark it on the wall, you get a tattoo, it stays. And then week after week after hour, you do your samples and you check them against that standard. Remember we talked about define, measure, DMAIC process? This is how we define our quality. And then we measure it by doing samples, and we analyze it by posting those samples onto our control charts. and then we take appropriate action if they're not within those boundaries. So let's try one of these problems. Here we go. Boxes of Honey Nut oatmeal are produced to contain 14 ounces of cereal with a standard deviation of 0.1 ounce. Okay, we've got some good information here. That tells me that my process, X double bar, should produce 14-ounce boxes. And the standard deviation of that process, because of the machine we bought and the boxes we buy and everything, should be, and that little O with a kickstand on it is a sigma, or the standard deviation is 0.01. Set up a 2 sigma X bar chart. 2 sigma refers to Z. Back in stats you learned about Z and Z tables. Don't worry too much about it, because we know that for our standpoint we just want to know what Z is. And in this case it's 2. In some problems it'll say give me a 3 sigma X bar chart, and in that case Z would equal 3. In this case Z is 2. For a sample size of 36, remember sample size in statistics is the small letter n equals 36. We have everything we need to solve this problem because we know our formula for the upper control limit, and our mean we know is 14. We want to know what the upper control limit is, and that would be our X double bar plus Z times sigma. Now there's a little issue here because this is sigma of the process, and if we're using samples, and this says it in the book, it says it in the problems, it says you have to make a slight adjustment, and so don't use this. Make a little change here, and we're going to do this. It's going to be this divided by the square root of n. So you have to make a little adjustment when you're doing samples. So let me plug in our numbers. That's 14. Z is 2. Sigma is 0.1. And n is 36. Let me go ahead and put the formula down for the lower control limit because it looks very similar. It's X double bar minus Z times sigma divided by the square root of n. So that's pretty simple. We'll plug these back in. That's going to be 14. Sorry, I'm not really good with this. Actually, I'm going to have to erase that. Give me just a second here. Let's clean all this up. Get this all back right. Here we go. Equals 14 minus 2 times 0.1 divided by square root of 36. And our answers then for this problem would be, look down here, 14, put it in your calculator, 0.03, and 13.97. We go over here to our control chart and we fill in the numbers. We now know our upper control limit. We know our lower control limit. These we will now use, and sure enough, part B, when the sample was taken at 10 a.m., we'll put 10 a.m. down here, the sample mean was 14.02, so the X bar, single bar, was 14.02. We plug that in, boop, right there. Using the 2 sigma control chart that you just built, what is your assessment of whether the process is in control? State as a sentence. Well, based on our upper control limit and our lower control limit and the sample that we just received, our process is in control. Now, if, for example, at 11 a.m. we went out and got our sample of 36 boxes and we weighed them and we got the mean of that sample and it was up here, we would run screaming into the plant and go, our process appears to be out of control because I'm above my upper control limit. What's going on? Are the boxes okay? Is the machine running okay? Is it overheating? Are the raw materials okay? Is the operator doing it correctly? Is the machine calibrated correctly? We would check everything, make any adjustments, and then at 12 a.m., or in that case p.m., go get another sample, and again, we'd hope it was back in line with what we had. That's where we use mean charts. Mean charts measure central tendency. Central, the mean. The mean of the samples. How do they fit within the control chart? A little different example I need to show you because there's a slight variation we have to be prepared for. Because in this situation, we had all the information. We knew that the process was designed, the machine was purchased to run 14-ounce boxes. And the standard deviation of those boxes should be no more than 0.01. We often do not know the standard deviation of a machine. If we don't know the mean, the grand mean of the machine, we could just take just a lot of samples and take the mean of the samples and the mean of the means. That's what X double bar is. It's the grand mean. It's the mean of all of the sample means. So we can estimate this. But if we don't have the standard deviation, we have to use a different process to calculate. Let's take a look at it. We're still going to do a mean chart. We're still going to take our samples and measure the mean of those samples. But the formula changes when you do not know the process mean or standard deviation. That's what happens most often. So we'll use a very different formula. Now we recognize this, but there's no Z and there's no standard deviation. So what we're going to do is we're going to use this, what we call R bar. R bar is the average range that the machine produces. So the range is different than the mean. The range is the difference between the largest and the smallest in the sample. So if we measured our boxes of cereal at 10 a.m., we would take the largest minus the smallest. That would equal the range. And if we did that for sample upon sample upon sample, and then we averaged them all together, the average range of our machine or our process is this. So we can figure out what the average range is the same way that we figure out what the average mean is. Then we need this crazy A2 value, and in another case, we'll look at it in a different video, a D4 and a D3. These are provided in a table, and I'm going to jump ahead to that table. It's a statistical table. It's like the Z table. They're everywhere. They either come in 3 sigma variables or 2 sigma variable or so forth. You can Google these. It's in your textbook, and I will provide it as I did here, and these numbers are always the same. So let's look at this problem, and we'll use the table. 35 samples of size 7. Be really careful on this. I did this intentionally because these trick people. What is N? Is it 35 or is it 7? Well, N is sample size. N is 7. We're taken from a fertilizer bag filling machine. Gosh, that would be fun to operate all day long. The results were an overall mean. That would be our X double bar of 57.75. An average range of 1.78. So, in order to calculate our upper control limit, we don't see the standard deviation noted anywhere, so it's kind of a sign that we should be using a different formula. We'll take our X double bar, we'll take our A2 value, times our R bar. 57.75, right? Plus, what's our A2 value? Well, it depends on your sample size. Our sample size was 7, so I'm going to go to the table, and it's a 3 sigma table. I'm going to go down to sample size N, sample size 7. Our A2 value is 0.419. 0.419 times our average range, 1.78. Put that in our handy dandy calculator. We're ready to go. I'm going to go ahead and put the LCL formula in. 57.75 minus same values. Plug those into our handy dandy calculator, and I get an upper control limit of 58.50. I get a lower control limit of 57. You don't always have to draw this. I kind of like to because it makes it a little easier to use sometimes. My upper control limit is 58.50. The mean I already knew was 57.75, and our lower control limit is 57. And as I like to say, we're off to the races. We are ready to calculate or to capture our sample and our 9 a.m. sample. We're still looking at central tendency, the mean of the sample. So we will grab all of our bags of fertilizer. We will weigh each one. We will take the average of that, and we will hope that it falls between our upper and lower control limits. And we'll do the same thing at 10 o'clock and 11 o'clock. And we will not change these values. These stay. We just keep taking samples. And if perchance it falls outside of the control limits, we will investigate. And we will fix things. And then we will go right back to taking samples. Give that a try in the homework problems. And I hope this video helps you kind of sort some of that